So I'm going to start recording now, and let's talk about this. We have two lectures, computational thinking, and then one of the specifics of computational thinking we'll look at after that, which is our pattern recognition. So today, computational thinking overview, and then pattern recognition, which is part of it. I've got a chat there which says yes. I think that's yes to my question, could they hear me? So computational thinking, we actually have, and you'll see in the notes there, there's a reference, and I think I even put a video clip in there from Jeanette Wing. Jeanette Wing is a sort of a professor at university in the United States who famously, I think in 2005 or 2006, she put a paper together trying to define the term computational thinking. So there's been a few people trying to define that for a while, and I guess the people are saying that her definition of it was maybe the best so far. And so that's one that we're kind of going to look at. So computational thinking, and she argues, and there's a paper that you're going to look at, which is going to be your lab activity for this week. So that'll be next lesson I have with you in the lab. You're gonna look at computational thinking from the definition that Jeanette Wing gave. So that'll be worth you looking at. And basically, if I was to summarize it, so she's saying it, computational thinking is something that everybody does. And so in computer science, we should be training, everybody should be learning computer science, just like everybody learns math and English, or in some other country, they might learn math and Arabic or math and French or whatever. So everybody should learn that because it's a way of thinking which is necessary for people to be successful in a modern life. Now, when I say in a modern life, that doesn't mean that everybody's going to go and write computer programs or that everybody's going to go and create computer networks. But what it means is everybody has to solve problems, right? And so that's what she's saying, is she's saying computational thinking is a way to solve problems. And the actual name of our course is computational thinking and problem solving, right? And so there you go. So it allows us to take a complex problem, to understand what the problem is, develop possible solutions. And I hope you can see that that doesn't have anything to do with being a computer or using a computer, right? You can do that without having a computer. So that's computational thinking, and that's what the focus of this lesson and some others that we'll do. So this diagram here on the right is worth looking at for a minute, and it's got some little diagrams that go with it. You'll notice that this is broken into 4 components. This is a model. This is a model of computational thinking that more or less relates to what Jeanette Wing was saying. But if you look at this model, you'll see that if we imagine the brain is the whole of computational thinking, that is made up of 4 components. Decomposition, which means whenever we have a complex problem, we can break it into smaller problems and then try and solve those. And this diagram kind of shows that kind of nicely. If you imagine that little red dot there, or it's not so little, it's the bigger of all the dots there, that represents a complex problem. And so how we would solve that is we break it into smaller, and we keep breaking it down. We actually used to call this in the 80s, we used to call this stepwise refinement, which is taking a big thing and breaking it down to smaller and smaller until we get to finally something where we can apply our technology to it, write a little program that will solve each of these little sub-problems, and then we can join them together and we've solved the problem. So that's decomposition. Whereas compose means to put together, so decompose means to break apart into smaller bits. Abstraction is what mathematicians do. Basically, it's taking something which is complex, again, complex problem, right? Taking something complex and stripping away everything except the absolute bare bones that we need to focus on. So it's determining what is the meat. Sorry, I was going to say the meat or bones or whatever. Maybe I'm hungry. I don't know. But what is the thing that we need to focus on? And then everything else we won't worry about, right? So that's abstracting. In mathematics, we do that. Like you got a problem, right? I have a problem which might involve, I'm traveling between Doha and Dukhan at 120 kilometers an hour. How long will it take me to get there if the distance is 80 kilometers, right? Okay, so you could do a mathematical equation for that, right? You could say, okay, well, 80 kilometers, would it be divided by or multiplied by? And you'd come up with the answer. You could do that with x equals y or y equals x something, right? You could do that. That would be your abstraction. In your abstraction, notice there wouldn't be anything to do with your car. There wouldn't be anything to do with the Khan. There wouldn't be anything to do with Doha. There would just be y is equal to x multiplied by. That's what we've done. We got rid of all the stuff that we didn't need to solve the problem, just focused on what we did need. That's abstraction. Algorithms, that's where we're going to do a step-by-step. Algorithm is like your recipe for cooking. I need to do this in this, I need these things, and I need to do it this, then this, then this, then this, then I get what I want. But that's your algorithm. We'll look at that later. Today, we're going to look at this one, which is 1/4 of that, which is going to be our, what's that? It's a pattern recognition. And the diagrams all show it, right? In this diagram, we see, well, that kind of looks like the face of a dice or something. But in any case, these two are the same. So we see the same thing repeating over and over again. Then what we can do is we can write a little program that does this. And then we can call that when we need it. And that's the idea of a function or a subroutine in a program. We'll be talking about that. There's no notes on this slide, so I'm just going to continue on. So computation, as it says, we include in computational thinking decomposition. I hope I discussed that okay for you, breaking up the big complex problem into smaller things that we can actually address. Pattern recognition, where we see something that's repeating. So we're going to write a little program that processes that, and then we can repeat that program. Abstraction, focusing on only the things that are really necessary and getting rid of everything else. Algorithm, step by step, solve a problem. Okay, so am I going too fast? You tell me. Then I'll know how much Red Bull I'm supposed to have and how much coffee, right? If I go too fast, then that's too much Red Bull and too much coffee. Just kidding. Computationally is not programming. So like I said in Wing's article, she's saying that everybody should study computing science, and computing science should be computational thinking. And it should be just a way to solving problems, not necessarily writing programs to solve the problems, but a way of solving problems by step, by these things, right? Those 4 things we talked about. Can you take a big problem and break it into parts, decomposition? Can you abstract it? Can you see patterns? Can you write algorithms? Can you do all that without using a computer and a computer program? Yeah, of course you could. And so that's what we need to focus on, is those things, and not on writing the computer program. If we want to make computational thinking universal, in other words, I guess what Wing was saying is, Wing saying, you know, universities should have in their first year of studies, everybody has to do this. You have to do math, you have to do language, she says English, but you know, so that's an American university, you know, Arabic, Spanish, French, German, whatever. You have to do a language, you have to do math, and you have to do computational thinking. That's what she's saying. She said everybody should do that. And even though you're not going to be a computer scientist, you should do computational thinking, because it is so rich in its ability to help you to solve problems, that everybody should do this. Does that make sense? So I mean, it's kind of like Polya. Is Polya in this lecture? I think it is. When we get to Polya, I'll try and sort of bring that in. All right, so we got an example. You're gonna go and meet with your friends, and you're gonna do something. And so first you have to decide what you're gonna do. And so you're gonna ask your friends, what do you prefer to do? You know, well, I prefer to go jet skiing today. No, I prefer to go and drive our cars and break them in the desert. No, I prefer to go and watch a movie, you know, or I prefer to go and get pizza. When you find something that you're going to agree on, and you know, how do you agree upon it? Is it because, well, the person that talks the loudest, that's the one that's whose idea will be, or will it be by voting, or you know, you'll have some way of deciding what you're going to do, or maybe you just all like to do the same thing. That would be really, really good. And then so you'll decide what you're going to do. That'll depend on a few things, like I said. So maybe you want to go jet skiing. Well, you know, it's middle of winter. It's 12 degrees out there. You know what? Maybe we won't go jet skiing. We'll go and drive our cars in the desert instead, because it's not a suitable time to do that. Likewise, the weather. There's a few. Well, I mentioned the weather. The traffic. There's a few things that would affect which of those decisions you did. So you do some planning. The planning might change because some inputs might change. Like I said, the weather might change. Somebody can't make it, might change, but you would do some planning to get there. That planning would be part of computational thinking. It doesn't mean that you're writing a computer program, does it? It just means that you're thinking in a way that you could give instructions to get something done, that maybe those could go into a computer. All right, so here's a thing that we're going to do. So some things that you might consider. Are we going to go jet skiing, or are we going to go to a movie? How much time we got? How much money we got? Going to go jet skiing, it's going to cost you, you either have to buy a jet ski or you have to rent one. It's going to be a couple hundred reals an hour. Don't want to spend a couple hundred reals an hour. I want to spend 35 reals. Okay, we'll go to watch a movie. I don't know. Can you watch a movie for 35 reals? I don't watch movies. I watch Netflix. What are we interested in? Based on that, we'll come up with some solution, right? So we're going to ask these kind of questions. Where could we go? Who wants to do what? What have we done before, which we liked? So we have some experience, right? I liked it when we went and broke our cars in the desert. Let's do that again. But, we'll break his car, not my car. That kind of thing, right? I don't know. Guys, I'm not making fun of anybody about breaking cars in the desert. I've broken more cars in the desert than a lot of people. So, I'm saying this about me, right? I've had my car on its roof. That's why I ride motorbikes now, because it's cheaper to fix them. And my friend, I used to be in a 4x4 club in Dubai, and that's exactly what we used to say. Let's go break our cars in the desert. I don't know why we said that. It was fun. But yeah, we tried not to break them too much. Thinking computationally on task 2. All right, you guys seen this kind of thing? Could this be thinking computationally? Plan, right? That word keeps on coming up, right? I want to get to here. So how am I going to do that? I'm going to plan, right? I don't know. I don't play games like this. My kids play games like this. So I would lose. But so you got some problems there. You probably want to know, well, how do I beat that? How do I get up there? All right, well, let's see. We got some answers on there. So let's see. And so down the bottom, the reason why I'm showing you down the bottom is there's some notes there that might be sort of become useful to us, right? So it says, what things do we need to collect? How do we collect them? How long? What kinds of enemies do we have? And if we knew those kind of things, so our plan has some inputs, and based on those inputs, we might actually change our plan. Okay, well, that's how it looks. So we need to know, what do we need to collect? Well, I need to collect this key. I guess I need to get this key to get through there or something like that. How can I collect that key? And maybe is there anything else? What kind of enemies I got? These skull things. How do I overcome my enemies? Do I have power to overcome my enemies? Maybe. So what we're supposed to do here is we're supposed to know that computational thinking is made up of decomposition, pattern recognition, abstraction, and algorithms. We're supposed to know that, one of these things relates to each of those things. So what would be decomposition for explanation? What's the explanation of decomposition? Decomposition. Oh, I see how this is supposed to work now. It's a cool thing, right? Decomposition, focusing on the important. Now that's not decomposition. What's focusing on the important? That would be one of these things. Somebody said abstraction. So I'm going to put that there. That's abstraction. Developing step-by-step solution. Very good. That's an algorithm. I'll put that there. Breaking down a complex problem into smaller. Decomposition. Very, very good. And looking for similarities. That's the only one left, right? Now, sorry, it goes underneath, but that's pattern recognition. All right, so decomposition, options of where to go. What do we got here? It's just, sorry, these things sit on top of each other. What you have previously done that have been a success in the past. Could that be pattern recognition? Would you agree? I'm going to go with that as pattern recognition. Would you agree? All right, where are you going to go? How are you going to get there? And what time you meet and go? What would be any of those? Where are you going to go? I would go with that. I reckon that's an excellent answer for that one. I'm going with algorithm, right? So we've done pattern recognition. We've done algorithm. We've got a couple more things to go here. What do we got here? What's that? Transport used to get to the location. Could that be and options of where to go? Got abstraction. Sorry. Options could be. Okay. I'll go with that. And then the last one would be, was that, have we done pattern recognition?
Yeah, I think it's abstraction.
Okay. All right, abstraction. Okay, abstraction would be just taking it down to the simplest thing. Yeah, all right. So that's kind of a weird one, but yeah. Creating a computer game. Explanation on how to complete the level. Would that be decomposition, pattern recognition? Ways of getting to the exit. I don't know. Location of the exit. These are including similar features used in, oh, similar features. That would be pattern recognition, right? We've seen this before, so we're going to do that. So that's going to be pattern recognition for that one. Explanation on how to complete a level. Would that be decomposition, abstraction of the exit? There's kind of, you know, ways of getting to the exit. Ways of getting to the exit, I think they mean by explanation of how to complete a level. Like a level is decomposition, or you might think, sorry.
I was talking about abstraction.
Explanation on how to get to a level. Well, location of the, I don't know. Those are kind of weird. Let's see what they say. Abstraction is ways to get to the exit. Explanation. Anyway, so there's some answers. And what they've done is they put them in this little table. I won't spend a lot more time on that. You can have a look at that later. But the idea is that we see that we are using over and over again these ways of computational thinking, and we're not writing any computer program, right? Computational thinking, we're just doing it in our normal life. And so computational thinking is a skill for normal life, according to Jeanette Wing. So yeah, hooray for Jeanette Wing. Okay, we good with that? All right, so what about decomposition? Decomposition is one of the four components of computational thinking. That was the one where he took the complex thing and made it into smaller things. So what about it? So this course's name includes problem solving. So there was a problem that's mentioned here, which was the problem of COVID. Now, down in the notes there's some other problems that people have that they don't use computers to solve, but you know, maybe you could. Maybe you could have a personal problem, maybe you have a marriage problem, a car problem, or a TV problem, money problem. You know, and you solve them, right? We like to solve problems. And you might say, no, wouldn't my life be better if we didn't have any problems? I don't know, you might get kind of bored. I talked about my friends and I used to go out in the desert and drive, and at least 50% of the time something would go bad. When I say something would go bad, you know, the tire comes off the rim, you know, maybe somebody loses their bumper, you know, some car won't start, some car starts on fire. I mean, all of these things happen. Do we hate it because those things happen? No, those things happen. Every time those things happen, you learn something by solving the problem. You know, we got that tire back on. You know, we had to jack the car up, and we had to maybe put some WD-40 in there. There are some things that we had to do, and so next time we feel better. We know how to do this now. So we actually like problems. You're going to have a lot of problems here at the college that we're going to make you have problems. We actually call it a problem, right? Or give you a project. That's a problem that you have to solve, because when you finish solving that problem, you're better at doing that than you were before. Because when you leave the college, what's your job going to be? Problem after problem after problem. And then you're going to know how to solve that problem. And then your employer is going to like you because you do that. And then they're going to pay you more money. Then they're going to give you a promotion, right? Because you can solve problems. So the more we do that, the better our life is, right? So we go in the desert, we break our sorry about that. Actually, it happened on the weekend. I'll show you a picture if you like. But, car on its roof. Wasn't mine. Yeah, we do that because it makes us feel, I don't like to use the word powerful, but yeah, it does. It makes us feel that we can do stuff when we find ourselves in a problem and then we actually solve it. It's a great thing. All right, so where do you start with a big problem? The problem's too big. That's the thing, right? The journey of 1,000 miles starts with the first step, right? So you have to take the first step. And the first step is we have to understand the problem. Well, the problem's too big to understand. Okay, so we're going to take a chunk out of that problem. That's our decomposition. We take a chunk out of that problem and sort of look at that and understand it. But yeah, the very first thing is we have to understand it. There's a reference here to IKEA. You get the IKEA box home and it's like, and so what do? You fish around and you find the notes. IKEA is very smart about its notes, by the way, because what I mean is IKEA is Swedish. Nobody understands Swedish except Swedish people. I mean, it's just a weird language. And so they put the notes out, and what do? Everything's in pictures with numbers, right? I mean, just, okay, well, obviously the first thing you do is number one, then you do number two. I mean, you can follow IKEA's notes. And the other thing that they do is really smart, is because they give the instructions with the thing, whatever you buy. But if you lose the instructions, it's no problem. The name of the thing is there, right? It's got some weird Swedish name. And so you just Google that and you'll find the instructions are on the internet and you can follow them there. So you always have the instructions. The instructions that I'm referring to in that IKEA gives you, that would be an algorithm, right? That would be an algorithm. And so it's an algorithm, but it's not on a computer, right? Well, you're looking at it on the internet, but I mean, it's not a computer program. Some things that the point of this slide is that not everything can be looked at through the eyes of just pure engineering or pure sort of mathematics or physics. I mean, some things we just need to use our sort of subjective, creative self. And so how that's going to be seen in our solving of problems is everybody's solution is going to have some little unique things to it. So even in our computer programming, people use different names for their variables. There's some little things about it that's going to be different. And so there's our human genius, I guess you could say, our human uniqueness comes through in the solving of our problems. If you're creative, that's a really good thing, that you can think of a new way of doing something. And sometimes that can cause a breakthrough. Because other people haven't thought of doing it in that way before, you actually get a better way of doing things. That actually is very, very important in developing of solutions. And so I finally come to this point, which is I mentioned the scientific method, and I mentioned Polya a couple of minutes ago, and so I want to just sort of dive into that a little bit. Scientific method we've had for a long time. I think since like Aristotle, so a couple thousand years. So Aristotle and Plato, they were talking about this. So scientific method, we form a hypothesis. So if you've ever studied science or talked to scientists, you'll understand this. Basically, a hypothesis is, I think that this aspect of the world can be described in this way. That's my hypothesis. So what I will do is I'll plan an experiment. And so from a scientific point of view, what our experiments are is we try and falsify our hypothesis. That is, that I said, I think that this particular thing about the world can be explained in this way. Now my experiment will try and prove that my hypothesis is wrong. And if I do the experiment and I've designed it properly, and I can prove the hypothesis is wrong, well, then I have to start again and do something else. But the way I design my hypothesis, I'm hoping that that I didn't prove it's wrong, but I'll try and do my experiments to prove it's wrong. If I can't prove it's wrong, then I'll publish a paper and say, look, this is a hypothesis. I did this experiment and I wasn't able to prove that it's wrong. So therefore, I think it's true. Other scientists, please have a look at my hypothesis. Can you prove that it's wrong? And so other scientists will look at that hypothesis and say, well, maybe that experiment wasn't that great. Maybe we could change the experiment like this, and maybe then we could prove that your hypothesis was wrong. And after, 10 years or whatever, and lots of scientists have had a go at it, nobody was able to prove it's wrong, then we're going to say, well, it's probably right. And so we're going to start referring to that hypothesis as being something that's probably right. I don't know, maybe 100 years from now, some other scientists will come along with much better experiments and they'll be able to show that it's wrong. And then we'll have to make a new hypothesis. You get the idea? But that's kind of what they do, right? They execute the experiments, evaluate the results, publish it. Other people look at it and they can do that too. What Polya was doing was a little bit different than that. Polya was saying, well, we could solve problems using something like the scientific method. And so now we're not trying to prove some idea is right. What we're trying to do is we're trying to get the solution to a problem. But I hope you can see that the stuff on the left is kind of like the stuff on the right. So one thing we do is we try and understand the problem. Now with the scientists, what they're doing is they're saying, I think I have this idea. I think this explains something about the world. What I'm doing here is I'm saying, I think that I have this problem, and I think that this is the problem. All right, so now I'm going to put together a plan on how I'm going to try and solve that problem. I'm going to do the plan. And once I've done everything I tried in the plan, I'll have a look at it and see if it's right. Planning seems to come up a lot in this when we talk about computational thinking. And so just a little segue on that here. I'd say that, yeah, one of the things that you'll study in your diploma or your degree is you'll probably study a little bit of project management. That looks a lot like project management to me, right? And you're given a lot of, so you'll do project management in a small form because you have little projects that you have to do. Imagine a life where your whole life was just spent doing projects. Quite possible in the IT business, quite possible. You'll have to do a lot of that planning. If that's an area that you excel in, you're really, really good at planning, then you could become a project manager. You could be a project manager and not write any programs. How do I know that? Because my daughter and my son-in-law, that's what they do. And it's a very, very nice job. I can tell you that they both earn a lot more than I do. And that's a trajectory for people who start off in the IT industry. They'll often go on to be project managers, but you don't have to be a programmer to be a project manager. What you have to be is somebody who can understand problems, devise plans, get all the things ready together for the plan. Kind of like manager is an important part of that word, right? It's project and manager. Maybe some of you like to do that sometime. I don't know. All right, so the idea of this slide is that in our projects, our problems, our computer problems, they may seem so big, so complex that we don't know where to start. And this is where the decomposition comes in. Don't be put off. Okay, so the interrelated problems, that means that it can be broken down into smaller problems. This means it can be decomposed. The other thing is, don't just jump in and start writing a computer program to solve a problem. If you haven't understood every component of the problem, you don't want to start writing the solution, right? You really need to do the first step first, which is understanding the problem. So I mentioned there's this concept of the project manager. There's also this concept of the analyst. So we have this concept of a business analyst. We have a concept of a programmer analyst. And what their job is, as you might guess from that word, analyst, analyzing the problems, and then coming up with solutions. What analysts will typically do is they will break a big project down into small bits. They'll draw diagrams which represent what they think the problem is and what they think the solution is. They'll show those to the people that want the program built for them, and they'll get their input on it, and probably those diagrams will change. The diagrams help them to understand exactly the details of the problems. Once that's totally understood, then they start making their plan on how they're going to build the system. And only after that do they start writing programs and stuff. So analysis is a phase that happens before design and before building a program. So the idea of what is undesirable, that's the current state versus the ideal state. So we have a computer system, or let's focus on computing here for a minute, though, even though Wing is sort of saying that this is for everything, not just computing. So we have a computer system that does X, Y, and Z, but we want it to do A, B, and C in X, Y, and Z. So our ideal state is to include A, B, and C, but we haven't really understood everything about them first. So first we'll go and try and dive in and understand A, B, and C. Now, once we understand them perfectly, now we have our ideal situation. Where we want to go to is to add A, B, and C to our system, which at the moment only has X, Y, and Z. And so then we'll have to break down each of those. A, what do we have to do to get A? What do we have to do to get B? What do we have to do to get C? That's our decomposition. We're gonna have some abstraction in there, write some algorithms, right? We might find some patterns in there that we can work with, but that's the idea. The idea is that right now we're not happy with the situation as it is. It doesn't have what we want. We want to be happy, so we're going to have to add some some functions to our life or to the system. And so how are we going to do that? That's defining the problem. So just making this, doubling down on this, going back to Polya. Polya was the guy who was saying that how we do our computer programming is kind of like our computer systems development, sorry, is kind of, or our problem solving is kind of like the scientific method. Yeah, understand the problem, make a plan, execute the plan, evaluate. So what we can do in understanding the problem is we can use diagrams. You will use flowcharts as you try and solve small computer problems. We use flowcharts, we use pseudocode. And we always do that before we actually start writing the programs. So that's a good thing to do. The purple stuff is the more important stuff, I guess. That's kind of like highlighted. Key thing is the goal defines what needs to be done. So we need to know what needs to be done. What is the ideal solution? We do that first. We don't worry about the designs until we have understood what it is that needs to be done. So I hope we got that point. Here's an example of a, so now we're going into the mind of a events organizer, you know, so project manager, events organizer, similar but different because well, it's similar. All right, so you want to organize an event. The event is going to be an academic event. So in the event, people are going to talk about some academic topic. So you're going to get some experts together, and those experts are going to discuss, and people are going to benefit from that, including the experts will benefit from each other. So you've got to start planning there. What would you start with? That's the question here. So spoiler alert, you'll start with the highest level. All right, you'll start with the highest level. Can you see there? What would be the highest level thing? And we'll do the lower level things last. Where would you start on those things? Would you start with the snack? Planning out the snack? No, because you could plan that out the night before, right? If you haven't got anything, you can always just get on Talabat, you know, I need 5,000 something, right? I don't know. You know, it's not something that is going to make or break the conference. And also it might be better just to plan that later, because after you find out who's going to be there, because maybe different people like different kind of foods, you could actually ask them what kind of foods they like, right? So maybe that'd be good to do much, much later. So where do you think you would start? Would you want to know how many chairs? Topic. So what do you, yeah, speaker chart, but you want to know the topic, because before you can do the speaker chart, you need to know who's going to be the speakers. And before you can know who's going to be the speakers, you need to know who's going to be, what's the topic, because different people can talk about different things. So you want to know the topic first, then you're going to know who's the speakers. Then you can start talking about where you're going to sit them and who's going to do the advertisement. Last thing you do would be, you know, getting the food together. You do need to get the food together. People need to be happy with the situation. Food makes people happy. But I mean, there's a lot of ways you could do that better by letting some time go by, right? To help you better define, purple is important again. Always write them. Yeah, okay. So now I go into motivational speaker mode. A goal not written is only a wish. You ever heard that before? All right, that's enough on motivational speaker. When you write things down, it's better, obviously. You're more likely to complete them, and you're more likely to understand them better too. By writing them down, you get to understand them better, maybe need to tweak them a bit. But yeah, definitely in computing, we need to write down exactly what we're going to do. We've got some fun things going on now. Decomposition tasks, got a policeman arriving at the scene of a crime. What are the kinds of things that you think the police would want to gather from that situation? Is the slide. So here we got a witness. So the witness basically saw what happened. The policeman is able to actually use his own eyes. This is a man, so I'll refer to him as him there. And able to see a broken window and something's missing from that room. There's some foot marks gone away, and there's a clock. So, okay, so if you were going to solve that problem as the policeman, there's some things that you'd want to know. And hopefully you've already sort of thought of this. You'd want to know that what was the crime? Okay, so somebody stole something. When was the crime? Well, somebody had that, maybe the witness noticed the clock when it happened. There's evidence there of the broken window and the thing missing. The witness can talk to you, and maybe there's a criminal who's done stuff like that before. Maybe you like to work at Subway. Maybe you don't. I don't know. Maybe you make sandwiches at home. But if the people that do work at Subway, they always going to use a sort of a dialogue with you, which if you listen to it carefully, you'd realize it's like an algorithm. It's step by step. What bread do you want? You know, do you want butter? Do you want mayonnaise or nothing? You know, there's a step-by-step process. They don't ask you what meat first. They ask you what bread first, right? Things have to be in a certain order. And then, yeah, there could be a repeat. Would you like 2 of those, you know? So, yeah, but there's an algorithm there, right? And this looks like an algorithm to me. Now, they're also referring to it as decomposing. And that brings us to the end of the first lecture. So what I'm going to do now is I'm going to stop the recording, and I'm going to set up for the next lecture, and I'm going to give you a break for like 5 minutes. Does that sound good? If you come back in 10 minutes, I'll already be talking. But yeah, so I'll be talking as soon as I'm done with this. I think it's